by Nicolau Saldanha from PUC-Rio, who will speak on the homotopy type of spaces of locally convex curves in the sphere.
Thank you. Thanks for the invitation. Thanks for the organizers. And okay, thank you. Yes. And before I begin the actual talk, I would say a very few words about how I met Paul. This was when I was finishing high school. I participated in the Math Olympiad. At that moment, I didn't know what I was going to do, what kind of career I was going to follow. And I participated in the Math Olympiad, so that was an encouragement. But then Paul was one of the people, perhaps together with Fred, the two people who encouraged me to consider doing mathematics and coming to PUC to take an undergraduate degree there. So, and Paul was, as always, very friendly, very kind, so that weighed a lot in my decision. So thank you, Paul, for being so friendly back then and always. During all these years, we have been working together in PUC. Thank you, and happy birthday. So what I'm going to talk today is it's topology. So I hope it's close. Well, it's mostly topology. It also involves differential geometry and algebra and other subjects. So I hope it will interest this audience, but it's not exactly the kind of thing Paul works with, but I think it's close enough. Yeah. So let me. Ooh, okay, yeah, it works. Let me explain the title. What is a locally convex curve? What does that even mean? So we are talking about curves in the sphere. So yes, yeah. So a curve in the sphere is a smooth function from an interval to a sphere of any dimension. Okay. When do we say a curve is locally convex? We say it's locally convex when you take this, you take a matrix with columns being gamma t, gamma prime of t, and so on, all the derivatives up to gamma n of t. Take that matrix, take its determinant. This determinant has to be positive for all t. Okay? So maybe you're wondering why is this called locally convex? Another term is non-degenerate. So maybe from a differential geometry point of view, you would expect it to be called non-degenerate. That's fine. It's synonymous. And the term locally convex is, I think, very suggestive if you think about the case n equal 2, which is already interesting. In the case n equal 2, a curve is locally convex if it's bending to the left. Okay, so it's convex in the most basic and elementary sense. Okay, or at least a convex hull of a short arc is to the left of the curve. Okay? So you can make similar statements about the convex hull of small arcs in higher dimensions. We're not going to try to do that, but here are some examples of locally convex curves in the sphere S2. Well, I mean, obviously this is a circle, not a sphere, because the screen is two-dimensional, but imagine this as a photo of a sphere, and then that curve is turning left, okay? So the first example is the boundary of a convex disk in the sphere, okay? This one self-intersects, but it's still locally convex. And this one self-intersects more than once. Okay? Yeah? So we all understand what we're talking about at least. Okay, good. So questions here doesn't mean interesting mathematical questions. It means questions you may ask at this point concerning the definition. Okay? So for instance, you may ask, why is it we are discussing smooth curves? Maybe you should consider curves of class CK or some other differentiability class. And the answer is, we don't really care. Or rather, we try not to care. And for most of the time, we manage successfully to say it doesn't matter. It doesn't matter. It won't make a difference. Actually, it doesn't work 100% of the time. When we get to a certain advanced point in the discussion, it will make a difference, and then we will prefer to work with sufficiently smooth curves because it will make the theory simple. Okay, but it doesn't really have to be actually smooth. It just has to be sufficiently smooth. Another silly question is why determinant greater than 0? Wouldn't it be more natural to say determinant different from 0? And in this paper, the author says it's different from 0. So the answer here is, well, this is just a question of, do you want two very similar connected components of curves, or are you happy to just look at the curves turning left and leave turns curving to the right as saying, well, it's the same thing, just take it as a mirror image. Okay, so it doesn't matter. Now, this question is a little bit more interesting. Shouldn't we be working in the projective, in the real projective space? Wouldn't the real projective space be a more natural domain for such curves? Yeah? And this makes a difference if you're discussing closed curves, for instance. Okay? And then we have to pay attention to that. But we will prefer to work as a, let's say, the favorite domain for the curves to be the sphere. And whenever we have to discuss, for instance, closed curves in the projective plane which do not lift to a closed curve in the sphere, we say exactly what I just said. It's a curve in the sphere which is not closed, but when we project it to the projective space, it's closed. And there exists there exists a similar definition in Rn, or Rn plus 1, or actually two related definitions. One if you think of Rn as a vector space, the other one if you think of it as an affine space, but we won't go into that because it's related but would confuse the discussion. Okay? And the silliest question here is why Sn and not Sn minus 1? Well, okay, I won't say why, but it's a source of confusion because both dimensions are important. Sometimes you wish you had chosen differently. Okay. So whenever you have a locally convex and undegenerate curve in the sphere or actually in some other space, there is this very important construction of the Frenet frame of the curve. Actually, we already hinted at that in the definition when we took all these derivatives. So what is the Frenet frame of the curve? We take that matrix. Let's call it W because it reminds us of the Wronskian. And do what some people call the QR factorization of that matrix. Okay, there are many other names for it. For instance, you can say you're performing an orthogonalization process in the basis of taking the columns. Yeah, there are many names for this. Yeah. And we are going to pay much more attention to the orthogonal part. That's why we have this fancy name for it. F is for Frenet, obviously. And we're not going to pay so much attention to the upper triangular part. Okay? But if we think of it this way, we may pay actually more attention to the curve F gamma itself than to the original curve gamma. And then we say it's a curve not in the sphere, but in the orthogonal group. And the condition for being locally convex translates itself in a very nice way. That if you take the logarithmic derivative is obviously skew symmetric, but it's tridiagonal. It's tridiagonal with positive entries below the diagonal and zero entries outside. Well, it's tridiagonal, so the entries are zero far from the diagonal. So that's also a very nice definition. But if you introduce it, first of all, maybe it sounds not sufficiently motivated. So we begin with a more geometric definition. And talking of motivations, we will mention there is a motivation coming from differential equations to study such curves. We will mention it in a little bit. But first let me say, what are the spaces of locally convex curves which we are proposing ourselves to study in this talk? Okay? So we now consider the curves in the orthogonal group, not in the sphere, because the group structure is so helpful. So nice to be in the Lie group. Yeah? And then we prescribed an initial point and an end point. Yeah? In the sphere, this would amount to specifying not just initial point and end point, but initial flag and end flag, or initial jet, maybe. Initial jet and end jet of the curve. Yeah? So let L cube is a space of curves which begin in a specified position, which without loss of generality we can take to be the identity, and end at some other specified position when we are particularly interested when that final position is also the identity, because this corresponds to closed curves, which is geometrically so nice. Or maybe minus the identity. If n is odd, minus the identity has a very interesting geometric interpretation. These are closed curves in the projective space, which when you lift to the sphere, they are not closed anymore. But we're still interested in them. We still want to know what the space is like. Okay? So this picture is the first important observation we make. Okay? It says the following, that if you take some other curve in the sphere and you approximate it by what I tend to call a phone wire. When if I say this to Paul, he will immediately understand what a phone wire is. Or indeed to anyone who is older than 50 or 40 immediately understands what a phone wire is. But for some students this requires a little bit of an explanation what a phone wire is. Okay, but a phone wire is something like that. Yeah, it goes around, 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 around. This is a drawing, of course, for n equal 2, but there exists a generalization of the concept of a phone wire for, well, the actual phone wire is in dimension n equal 3, not 2. And it works for, not just for phones, but here for this construction. And there exists a generalization, an easy generalization for arbitrary dimension of what a phone wire is. And what is this saying? This is saying that if I draw a curve, a smooth curve, which is not locally convex in the sphere, I can construct a curve which in the C0 metric in the sphere is very near the original curve. In the C1 metric, it's very far away because you insert loop along the curve. And you end at the exact position you want, and it's locally convex. Okay? So there's this big factory of examples, and it tells us that if you begin with a curve which is not locally convex, there exists friendly, whatever, C0 nearby curve, which is locally convex. Okay? So in particular, the space is always non-empty. This is not working exactly. Oh, thank you. Thank you. So these are the spaces we are interested in. These are the spaces LQ. You specify a beginning and an end, and you want to know what the space of curves beginning there and ending there is like. Okay? Now, a little more motivation, as I promised. I mean, the geometric motivation may be sufficient. Well, for this audience, perhaps geometric motivation is the best motivation. But when I'm trying to convince people who are not from geometry and topology that this is an interesting problem, I point to this. This is interesting for analysis also. If you're studying this ordinary differential equation, the most basic and important ordinary differential equation in the world. It's a linear, homogeneous, ordinary differential equations. But the coefficients are not constant, otherwise we would have learned how to solve it as undergraduates, but otherwise it's very important, very basic thing. Now, if you take the fundamental solution of that differential equation and do this, you obtain a locally convex curve. So questions about differential equation translate into questions about locally convex curves. So, for instance, the space Li of closed curves, it corresponds to the space of potentials. The potentials are the h's here, the coefficients, okay? The space of potentials for which all solutions to this differential equations are periodic, for instance, 2 pi periodic maybe. Okay, so that's an interesting question in differential equations. So if this related to storm theory, if you consider the case n equal 1, you have an ordinary differential equation of order second order, and then you're studying storm theory. When do we have periodic solutions, that kind of thing. So what we're doing here can be considered, we're trying to do storm theory for higher order differential equations. Okay, so I is a space of is homeomorphic to the space of potentials, for which all solutions of this differential equation are periodic. Great. So when we say locally convex, you may ask yourself, do we have a concept of a convex curve? And yes, we do actually. And the concept of a convex curve is one of the first important remarks in this theory. That if you have a sufficiently short arc, it's convex. For instance, let's imagine we are in the sphere S2 and we restrict ourselves to locally convex curves. If you begin with a curve with a self-intersection, you can create more and more self-intersections. You can make that curve very complicated by deforming the curve. So you are in the same connected component. A curve with one self-intersection is in the same connected component as a curve with 1,000,001 points of self-intersection. But if you start with a curve with 0 points of self-intersection, a simple closed curve, if you deform it, maybe you believe this. I mean, it's the proof is non-trivial, but it's intuitive, right? If you start with a locally convex curve, which is also a simple closed curve, and you do this, if you keep it locally convex, it stays simple. You cannot create self-intersections. Okay, for instance, you cannot do this and go around the sphere without here creating some point where it's not locally convex. Okay, so the concept of a convex curve is an important concept. And the general definition, one general definition is this. You count intersections with any hyperplane. Okay, you count them with multiplicity. And the number of intersections has to be at most n. So a locally convex curve is, well, a locally convex curve. It means that if you take small arcs, they are convex in this sense. Not just in the sense we defined in the first slide, but in the sense that small arcs satisfy this property. So for n equal 2, a closed locally convex curve is convex if and only if it's simple. Yes? And for any q, meaning any final position you specify, there are two possibilities. Maybe there exists no convex curve ending at that point. Or maybe there exist convex curves. If there exists a convex curve, the set of all convex curves forms a contractible connected component of the set of locally convex curves. So if you deform a convex curve, it's still with fixed endpoints, it remains convex. And if you and that space of curves is contractible. Yes? No? Why contractible? Well, it's non-trivial, but it's believable, I think, right? Imagine you are in the sphere S2 and draw an arc of circle. Okay? Now take this initial point and this final point. So you can draw other convex curves here. But if you put axes in the correct position, these are graphs of functions. So it looks very believable that you can organize things in a certain way so that it's contractible. Okay, but it's non-trivial. I mean, I'm not, but it's not a proof. But it's just helping the intuition. Okay. So, okay, maybe it should begin to make some historical remarks here. The first questions which were addressed and answered were, of course, it's natural, what are the connected components of locally convex curves? And this was completely solved before I ever got interested in this problem by other people. But in order to explain the answer, I'll make first some remarks. LQ is a space of locally convex curves with prescribed initial and final point in the orthogonal group, or in the sphere, initial and final jets in the sphere. Q is an orthogonal matrix. The beginning, we begin with the identity, because if we are in a Lie group, we can translate things. Beginning at identity and ending at Q, correct. Yes? And we are particularly interested, but not exclusively interested, in the case Q equal identity or minus the identity. Yes? So, I want to argue that the space always has at least two connected components. Yes? And the reason for this is this, that the fundamental group of the orthogonal group is Z mod 2. It has a double cover, which is also its universal cover, which is a spin group. Yeah? So if you have a curve in the orthogonal group, you can lift it to the spin group. And that endpoint Q now becomes two possible endpoints. Let's call them Z and minus Z. And both are possible because of the phone wire construction. Yeah, because the phone wire construction also works in the spin group. So both are possible, so we have at least two connected components. Oh, and remember, there's also this remark that if there exists convex curves, they also form a connected component. So we our guess at this point would be two connected components if no convex curve exists, three connected components if convex curves do exist. And that guess is correct. So this is this theorem. So Little proved the case n equal. He was only interested in the case n equal 2. Apparently, only interested in the case n equal 2 and closed curves. So he proved, in our language, he proved the case n equal 2 q equal to I, but he doesn't use this notation, of course. Convex curve.
I'm puzzled by the vocabulary.
Convex, or for closed curves, it means, in the sphere S2, it means simple. Yeah.
So convex curves means convex, simple, closed.
In the sphere S2.
Not simple, but not closed, but simple.
Well, they all, if Q is equal to identity, they are all closed. Because you're ending at the same point you started, so it's a closed curve.
But then it's not the same to say that the curve is closed in the group, in the Lie group, or that it is closed on the sphere.
No, I'm sorry. Closed means closed in the group. Okay. So if the curve does this, I don't call it closed.
In the group.
If the curve does this in the sphere, it means in the group it doesn't end at the same point because the derivative is different.
Yeah, but what if
But
the curve
also in the sphere, you would perhaps not want to call it a closed curve because it has a point where it's not smooth at all. It has a sharp angle.
But
So that's not what we usually call a simple closed curve, right?
What about the fact of coming back to the same point? You include the point in the, sorry.
I don't understand your remark, but should I continue? Okay. Okay, so theorem here, Little in 1970 only considered the case n equal 2, only considered closed curves, but he already proved the result exactly the way we stated it, that there exists a connected component here, this picture. That there exists one connected component for convex curves, which in this case means simple closed curves. And there are two other components which you can tell them apart in general by lifting to the spin group. And in the case n equal 2, you can also tell them apart by counting number of self-intersections. Okay, and checking the parity is even or odd.
And in this case, which is a component corresponding to convex curve, to convex?
This is convex. Well, that's what we call a convex curve. There was this definition that we count intersections with hyperplanes. It corresponds to this picture. It corresponds to being, well, if you want to really relate to the usual sense of convex, it means it's a boundary of the intersection of a convex cone with a sphere. Is that clear? Yeah. But we also count half of this curve, for instance. We also count that as convex. Okay, so there exists a concept of a generalization of the concept of convex curve, which makes sense for curves which are not closed and makes sense in higher dimension. Yes? So let's go back to phone wires, because of this concept of a phone wire. How much time? How much time?
15 minutes?
15?
Yes.
I have more 15 minutes, yes. Okay. So adding loops is like the phone wire. If you have a curve which is not convex, you can add loops like this. So here we are in the sphere S2. We have a point of self-intersection. So what you do is you stretch it, go around the sphere, and the whole time it remains locally convex. And at the end of the story, you gain two little loops here. So you may add loops to a curve which is not convex and turn it into a phone wire. Yes? But question here, and remember the title of the talk was what is a homotopy type of these spaces. Yeah, we haven't really gotten to that yet, but we will. And a crucial question at this point is, okay, for convex curves we cannot add loops. For other curves we can add loops. But how about if we have a family of curves which are locally convex but are not convex? Can we add loops to the whole family in a uniform way? because if we could do that, then the answer would be easy. But we cannot. So there exists a higher dimensional version of the concept of convex, if you will. There exists families for which you can, for each individual curve, or even for large subfamilies of curves, you can add loops. But you cannot do that for the entire family. Yes? And therefore, the homotopy type of the space of locally convex curves is not going to be your first guess, or your guess at this point of the lecture. Your first guess at this point of the lecture would be something which is, in fact, a decent approximation of the answer, but it's not the correct answer. So, consider a locally convex family of closed curves. Can we add loops uniformly? And the answer is no, and it's, show me the, para baixo, pro polo sul, parte de baixo da figura, aqui assim, aqui. Sobe ela tudo, sobe tudo. Não, sobe, não diminui. Então deixa assim. Okay, so here is, well, it took me a long time to understand this picture, okay? So if you are confused, well, it's normal thing. But this is a picture of a family of curves which are not convex, but they are not simple. And you can add loops to an individual curve. In fact, you can, this is parameterized by the sphere S2. So it's an S2 family of curves in S2. Okay? The way to interpret this picture is like a world map, the Mercator projection, where you have this. This is identified with this. You may notice that this curve is the same as this curve. Yes? At the South Pole, we have a circle drawn twice. 1, 2. At the North Pole, can we see the North Pole, please? At the North Pole, we have a circle drawn 4 times. 1, 2, 3, 4. Yes? And the 2 edges are identified. This family of curves, we can add loops provided you remove 1 point. It's enough to remove 1 point. But for the entire thing, you cannot add loops. Yeah? And the reason is that you can construct a submanifold of codimension 2, which is intersected exactly once, which is a set of multi-convex curves. In this case, I guess I would call them biconvex curves, which is the South Pole, which is curves which do this, but not just this. So let's go back to the talk, please. No, we cannot add loops uniformly here, and let's discuss why this is true and what consequences it has. So what are the spaces LQ like? So one related space is a space of loops. Forget about local convexity. Take any curve in the orthogonal group. Now that space is well known. That space is omega SON, SON plus 1. That space is well known. Yeah, good. So the construction of F gamma defines an inclusion. We can consider locally convex curves as a subset of this set XQ. And the adding loop constructions, when you look at it with a little attention, it becomes clear that if you look at any homotopy group, that is surjective. This inclusion becomes a surjective map. And also for homology. But if you look at cohomology, well, the arrow reverses, and this is injective. And the question then would be, well, are these maps bijective? Being bijective, it would be bijective if we could add loops in a uniform way, but we cannot. But
sorry, you mean for each k? Who is k here? Your integer k.
Any k. K is a natural number. So if Q, well, okay, maybe this requires a remark here. There exists a way which I'll not discuss in 1 minute or whatever, but it's not hard, to reduce any orthogonal matrix to some diagonal matrix. Okay, so it suffices to answer the question for diagonal matrices. Now, if we look at diagonal matrices, the matrices plus or minus identity are clearly very special. For any other diagonal matrix, the answer is yes, yes. And then we understand the space LQ. It's just like the space of loops in the orthogonal group. But if Q is equal to plus or minus identity, then no, it's not the same, because of the kind of difficulty shown in the figure. Okay? So let me explain this a little bit more carefully. First, for the case n equal 2. So what is a multi-convex curve? So a multi-convex curve is, well, the concatenation of many simple closed curves. So you have times T0 is 0, T1, T2, up to Tm, such that at T1 it's identity, at T2 it's also the identity. But each arc from Tk to Tk plus 1 is convex. So it looks like this. That's a multi-convex curve. Okay? So counting intersections with a submanifold of multi-convex curves gives us a new element in homology or cohomology. And if we work this out carefully, we arrive at the homotopy type. So let's try to formulate this with a little bit more carefully. If we remove the multi-convex curves, let's call this auxiliary space Y, then the inclusion of Y and X is a homotopy equivalent, meaning then you can add loops in a uniform way. But you have to put back the multi-convex curves. And now the homotopy type is going to change. And, well, we have to answer, of course, the question of how do they fit in? And they fit in a very nice way. They fit in a very nice way because there exist maps from the sphere S2K to Li, which intersects the set of codimension. This is a manifold of codimension 2K, okay? Exactly once. Does not intersect the other guys. It's homotopic to the identity if a loop is added, but it's obviously not homotopic to the identity because it only intersects that manifold once, okay? And it's also homotopic to the identity if you look at it in the space X instead of the space Y. So this is a statement of the homotopy type for n equal 2. You start with a space of loops here, and then you have to add this infinite bouquet of spheres. Okay, this S2 here is the drawing we saw. The drawing we saw was dimension 2. We can generalize that drawing to any even dimension to obtain this, 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 and this sphere. Okay? How many minutes do I have? 5? Yeah. So this is a result for n equal 2 for the sphere S2. This is a paper which I published a few years ago, but we didn't stop there because there's a natural question of what happens for other values of n. What happens in S3 and in Sn for larger values of n. In order to proceed, we needed actually to invent a lot of algebra and to discuss questions in the combinatorics of the symmetric group. So it would require a very long time for me to give a decent explanation of what's going on. So I'll just go over statements of results. Okay. By the way, we do have very recently, it's breaking news this year, we have a statement like this for S3. For S4 and higher, we do not have a complete statement, but we do know that it begins this way, so to speak. So you begin with a space of loops in the sphere, and there's some other stuff. But we don't understand the other stuff all that well at this point. Okay, but we know it's not just the space of loops in the sphere, in the orthogonal group, actually. But this S3 here is a spin group. Perhaps it would be less confusing here to write spin here instead of S3. Okay. So, just a statement here, this is a hard theorem. If you look at any diagonal matrix except identity and minus identity, then you can add loops uniformly in families. We don't have that nice phenomenon of that picture which we saw. That doesn't happen. Okay? If Q is equal to plus or minus the identity, well, the inclusion gives us an approximation of the homotopy type, but it's not the correct answer. Okay? At least we know that, but it's not the correct answer. For n equal to 3, we do have the complete answer, which is this. And draw 4 connected components because you have identity and minus identity, and for each one you have to lift to spin, so you have 4 connected components. Okay? And K takes a value 0, 2, 2, and 4. So we have these bouquet of spheres. This in fact means that there are 2 connected components which are homotopy equivalent to one another, but you only learn that in a very roundabout way. It would be nice to have some more direct proof of this. Maybe such a proof exists and we haven't seen it. Okay, so bouquet have 1 copy of SK, 2 copies of SK plus 4, 3 copies of SK plus 8, 4 copies of SK plus 12, and so on. Yes? n equal 4, we don't know. Okay? Okay, Bruce, I guess I'm out of time, right? Basically. Yeah, so I used this material for longer talks where I had more time to explain. So let's pass over this very quickly, and if you want to jump and ask a question here, you can. The way to discuss things in higher dimension is to introduce this concept of the itinerary of a curve. So the itinerary of a curve looks like this. You do the Bruja decomposition, and you pay attention to this permutation here, sigma of t. Yes? So when sigma, in generic points, sigma is the identity. So you have to pay attention when it's not the identity. Therefore, an itinerary is a word with letters in the symmetric group, but not the identities. Identity is trivial. We don't put it in. And, well, the L can be written, let me advance here. This is too technical. Yeah, but this is nice to state this theorem. The set of paths with a certain prescribed itinerary is always contractible. It's always a submanifold with a dimension which we understand what it is, and it's always contractible. And they fit together in a nice but not all that nice way. So here are some examples of itineraries. So when you have a locally convex curve in the sphere like this, you have to pay attention to when you cross the equator and when the tangent line to your curve passes through E1. Yes, you have to pay attention to that, and you have to pay attention to maybe something even more special happens. Maybe your curve is tangent to the equator at some point. And the way to take note of special events is by permutations. There's a permutation for every possible special event. Then the strata corresponding to itineraries, they fit in not all that nice way, but it's nice enough to allow us to construct a kind of dual, like Poincaré duality. And it's a CW complex. A CW complex with one cell for each possible itinerary. Now, we would like to understand this CW complex because it has the same homotopy type, but gluing instructions are hard. So in this picture here, we see how itinerary changes. And the concept of a parity alternating permutation becomes very important. And we generalize the concept of M and Y. It's not so nice anymore. And final questions, what is Li like for n equal 4 or higher? We don't know. How can we compute boundaries in this CW complex? We know only very partly. And here are the references, and happy birthday, Paul. These are locally convex curves.
So is there any question in the audience? Yes, Gael?
Can the H principle help?
Oh, yeah, sure. H principle is adding loop construction is H principle. So the adding loop construction is related to the following famous constructions. The H principle, Smale's method of studying similar problem, but for immersions. And Thurston's method of that's that famous video of the turning the sphere inside out. Corrugations, yes. These are all basically the same idea manifested in slightly different cases. So the H principle is indeed very important here. And in fact, let me make something of a confidence here. For a time I was worried that what I was doing would be trivial if someone understood the H principle better than I did. So finally, I got around to understanding enough of the H principle that not all that well, it's a hard subject, but enough that I feel confident that yes, it is an important tool, and no, it doesn't make everything trivial. It helps, it's important, and it's not just my ignorance of the H principle which is preventing me from answering all the other questions. Yeah.
I have a question myself, actually. At the beginning, you made the question said, why smooth and not seke? My question is not, why not just continuous? And to answer my question is because, you know, there's the theory of Anosov representations of surface groups into, so which is many people studying that, starting from Laborie, and there's a notion of hyperconvex representation, where the limit curve will be convex, locally convex, and even convex, you know. And for example, we consider the space of connected components of these representations. So maybe there is a connection between these works.
Maybe, yeah. I don't know all that much about the stuff you mentioned here. I would like to know more about that. But let me point out where in our discussion it becomes important how smooth the curve is, which is here for this theorem. Because, well, the theorem is correct for any degree of smoothness. We're talking about itineraries here, okay? But if you make your curves only very low requirement in terms of smoothness, it means these pieces, they don't fit together all that nicely. And you have a very complicated picture. If you say that curves have to be sufficiently smooth, it's still complicated. It's still not true, for instance, that we have stuff like this. Okay, one set of itineraries, it doesn't stop at something of higher codimension. It comes here at the middle of some other set of the same codimension. So it's not as nice as you would want, but still it's much nicer than what you have if you say, oh, who cares about smoothness? Let's just assume the curves to be.
But I think we have similar considerations to it. So if it's like hyperconvex means that there's some way if you have endpoints going, but how the tangent lines, they have some conditions like that. It's not completely free, but okay, but it becomes technical, but they don't ask for smoothness, but for the way that how the tangent lines will converge when the one point is going to one point. But
well, we want at least a curve to be continuous in the spin group or orthogonal group, right? Otherwise, we really lost control of things. But and for many of these results, it makes no difference at all. No difference at all. But here it does. Here it does. The strata are much nicer. if you work with sufficiently smooth curves. And the homotopy type does not change.
Is there any other question? Okay, so let's thanks once again.
Thank you. Happy birthday, Paul.